Hello, in this video we're going to take a look at a few important continuous time signals. The first signal is the unit step function denoted u of t and is defined to be equal to 1 for positive time t. So a simple sketch of u of t would look like the following, and this is amplitude 1. The unit step function is often useful for calculating what is referred to as the step response of a system. For instance, what comes out of the system with the output of the system when I apply my input starting at time t equal to 0. I can also use the unit step function to express portions of a function. So as an example, e to the minus 2t times u of t would simply define the exponential function for positive time only. So this is a sketch of e to the minus 2t times u of t. I can also use the unit step function to define more complicated types of functions. So here's an example where I have my unit step function delayed by 2 units of time and my unit step function delayed by 4 units of time. And if I take the difference, for t less than 2 or for t greater than 4, I'm going to have 0. But for t between 2 and 4, I'm simply going to have unit amplitude 1. So I can use the unit step function to define a square or a rectangular pulse. Another important function is the unit impulse function denoted delta of t. Delta of t is not given explicitly in terms of an analytic expression, but rather by its properties. The two properties of the delta function, or the impulse function, are as follows. It is defined to be 0 for all time not equal to 0, and if I integrate the impulse function over all of time, I get 1. So I can visualize my impulse as simply a rectangular pulse with a base or duration of epsilon, an amplitude or height 1 over epsilon, and it has unit area, and I consider the limit as epsilon goes to 0. So this would be the visualization of my impulse function and the visualization of the impulse function in terms of a rectangular pulse. A few important properties of the impulse function are as follows. If I multiply a continuous function phi of t by the impulse function delta of t, I'm simply going to get my continuous function evaluated at time t equal to 0 multiplied by delta of t. I can consider multiplying my continuous function by a shifted version of the impulse, delta of t minus capital T. In this case, I'm then going to have my continuous function evaluated at capital T multiplied by delta of t minus capital T. In other words, I take out the portion of my continuous function multiplied by the time, or evaluated at the time where the impulse function is located. I then have the sampling or the sifting property. So if I integrate the above expression, phi of t times delta t minus t, then I'm simply going to get phi of capital T, my continuous function evaluated at t. And I can see this simply by making use of the above property, because this integral is simply going to wind up being phi of t, delta of t minus t, integrated over all of time. And then I can take out the constant term phi of t, and now I'm integrating my impulse over all the time, which we know to be equal to 1. The delta function, or the impulse function, and the unit step function are related. So in particular, if I were to integrate from negative time all the way up until capital time t, the impulse function, I will wind up getting the step function. Or if I were to differentiate the step function, I'm going to get the delta of the impulse function. Let's take a look at an example. We want to find the derivative of the function x of t, where x of t is equal to e to the 2t multiplied by u minus t minus u minus 3t. Let's begin by doing a quick sketch of x of t first of all. X of t will be defined between t equal to 0 and t equal to minus 3. So just note that I have time reversal over here. At time t equal to 0, I'm simply going to have 1, and at time t equal to minus 3, I'm going to have the value of it over here of e to the minus 6. So now, if I want to calculate y of t, I'm going to differentiate this function. So this is going to be the derivative of e to the 2t times u of minus t, and I'm going to subtract the derivative of e to the 2t times u of minus 3 minus t. So this is going to be 2 e to the 2t times u of minus t. And then I'm going to subtract from this e to the 2t. The derivative of the step function is the impulse function, so this is delta of minus t. And the minus sign here comes simply from the derivative of the negative t here. So this is then going to be, I'm going to then subtract minus 2 e to the 2t, u of minus 3 minus t. I'm going to add e to the 2t, delta of minus 3 minus t. I'm going to group a few terms, so I'll have 2 e to the 2t, u of minus t minus u of minus 3 minus t. And I'm going to have minus e to the 2t delta of minus t plus e to the 2t delta of minus 3 minus t. If I look at this, this is exactly equal to x of t. So my derivative y of t is going to be 2 times x of t. Now if I look at this term over here, I make use of the fact that phi of t times delta of t is equal to phi of 0 times delta of t. So this is going to be minus e to the 0 delta of minus t. And if I look at this term here, phi of t times delta of t minus capital T is phi of capital T times delta of t minus capital T. So in this case, I have minus 3 minus t. So this is going to evaluate out to e to the 2 times minus 3 of delta minus 3 minus t, or e to the minus 6 delta of minus 3 minus t. So this is going to be my derivative y of t. It's going to be 2 times x of t minus delta of minus t plus e to the minus 6 of delta of minus 3 minus t. Now, if I were to do a quick plot of y of t, again, y of t is going to be defined between time t equal to 0 and time t equal to minus 3. It's going to be twice the value of x of t. So in this case, I'm going to have amplitude 2 here. And over here, I'm going to have the value 2e to the minus 6. But on top of that, I have the presence of an impulse at time t equal to 0. So I have a negative impulse here. And I have another impulse defined at time t equal to minus 3 with an amplitude of e to the minus 6. So this is a sketch of y of t. The last important function is the complex exponential signal e to the st, where s is a complex number given by sigma plus j omega. I can write my complex exponential signal e to the st using the real and the imaginary parts of s. So it's simply e to the sigma t multiplied by cosine omega t plus j sine omega t. S is referred to as the complex frequency, omega is the frequency given in radians per second, and sigma would simply be an amplification constant. The properties of my complex exponential signal depend on the values of omega as well as on sigma. In general, if sigma is negative, I'm going to have an exponential envelope that's decreasing in time. If sigma is positive, I'm going to have an exponential envelope that increases with time. The following plots show the different types of complex exponential signals that I can have. If sigma is equal to 0, I'm going to have a constant amplitude or a constant envelope. And I'm simply going to have, inside the envelope, a sinusoidal variation. If omega is equal to 0, so the complex exponential signal is actually a real exponential signal, then I'm simply going to have an exponentially increasing envelope, a decaying envelope, or in the case where sigma is equal to 0, I'm going to just have a constant function. And then, of course, if omega is not 0, then if sigma is 0, I'm going to have a decaying envelope with a sinusoidal variation. And if sigma is positive, then I'm going to have a sinusoidal variation with an increasing envelope. We could think of the complex frequency plane as follows. S is equal to sigma plus j omega. So the complex frequency plane, we sometimes also refer to as the S-plane. The x-axis is going to be given by the real values of S. The y-axis will be given by the imaginary values of S. And now, we can associate the different behaviors of our complex exponential signal by simply looking at our value of S. If we're in the right half plane as an example, then we know we're going to have an exponentially increasing signal. If we happen to be in the left half plane, that means sigma is equal to 0. Then we'll have an exponentially decreasing signal. If you have any questions, please send me an email.